You can tell by the title of my talk that I have a habit of reusing talks, partly because I'm lazy and partly because the talks are still kind of relevant. So this is the 3.0 of this talk, Navigating LLM Deployment. And I'll also give a brief history before I dive in. First, I'll start with hello, I'm Meryem. I'm the co-founder and CEO of TitanML. We are an AI inference stack specifically for self-hosted deployment. So clients that want to deploy AI models on-prem or on VPC. That links to my LinkedIn page if you want to connect. So today I'm going to talk about three things. If you want to have a nap, you could take a picture of this and then have a nap and then wake up in about 20 minutes time. And that's pretty much all that I'll talk about. So I'm going to talk about inference systems, which often gets confused with inference engines. And I'll talk a bit about why they're different. My talk today is focused mainly on scaling within inference systems. And I'm going to be talking about why traditional scaling methods just aren't really appropriate for AI workloads. Teaser, it's because they're GPU bound, not CPU bound. And then thirdly, I'm going to talk about how we built our scaling at TitanML, and we use proxies like QTime in order to do this. And I'll talk about why this has worked really, really well for us. But before I start, I'm going to give you a very brief history of this particular talk that I've given. And I first gave it almost a year ago, I think a year plus or minus a day at QCon in London. And the talk was called the same thing. It was called LLM Deployment, Tips, Tricks, and Techniques. But it was focused almost entirely on the inference engine. And the inference engine is essentially everything that you need to be able to get model weights and hardware and turn that into a static endpoint that you can inference. And that talk was focused around how do I design my inference engine such that I can deploy my first couple models, so I don't mess up my first couple deployments. I was then hoping I would be able to use the exact same talk 6 months later at QCon in San Francisco, because I was hoping I would be able to limit the amount of work I did. But unfortunately, so much in the ecosystem had changed, I had to pretty much rewrite the entire talk. Now, the talk I gave in QCon in San Francisco was also focused on the inference engine, focused on how you get essentially your model to work on your GPUs. And the focus of that talk was how can you optimize your inference engine, given that you know a little bit about your workload. So, for example, how would I optimize it for a low latency environment versus if I'm trying to optimize costs? Now, I think I've moved on a little bit from that. So this talk is not about the inference engine, and it's my first talk that I prepared, which is about inference systems instead of the inference engine. We're moving a layer up in the stack. And this is me. This is I didn't get ChatGPT to make this clearly. But the question I'm answering today is, once I have my inference engine, how do I scale it? How do I scale it up and down? So that's what today will be about. At some point in the future, potentially on Mars, I will be doing another talk about another part of the inference stack. If you have thoughts on what would be interesting to cover next, I'm all ears. So firstly, let's talk about the difference between inference engines versus inference systems. This gets confused a lot, I think, by the market when people just think an inference system is like, oh, well, isn't that just VLLM or OLAM or something like that? And there's actually a lot more to it than that. So here is a representation of what an inference engine is. Well, an inference engine gets you from my model weights over here, so some kind of open source model, maybe Llama 4 model that just came out, some hardware that I deploy it on, and then my inference engine turns that into simple, non-fault tolerant APIs that I can start inferencing. So this is a screenshot from our own product, but you can use things like, we have our own inference engine, but we also have backend support, things like VLLM that Alex was talking about earlier. And SGLang is another very, very high performance inference engine. If you're deploying on things like Mac, you might want to try out things like Ollama. But this is what an inference engine is. It's essentially the bare minimum that you need to be able to get an AI model inferencing. But that's super, super different to an inference system, which is much, much, much bigger concept. And essentially everything that's required to scalably and safely inference AI models in our case, in the enterprise, but really at any reasonable scale. And there's much more in that than just your inference engine. Well, the first thing is that I might have multiple inference engines. The inference engine that I'll need to deploy an embedding model is very different to a language model, which is different to if I'm going to deploy it on AMD versus NVIDIA, et cetera, et cetera. So in my enterprise deployment setting, I have n number of inference engines, not just one, or inference containers. I then have up here, I have my scaling layer, my load balancing layer. I have things like my logging and monitoring, alerting. And in this case, I've made all of these just very pretty white boxes, but actually each one of these is very, very complex. Today, I'm focusing on this tiny part of the inference system, which is auto scaling. And I'm going to be talking about how you can build scaling of AI models or LLM models in particular to mean that you get better application performance. So why do you need to scale? This might seem pretty obvious, but I'll go through it anyway. So reasons why you might need to scale. You only want to pay for the GPU time that you're using. GPUs are very, very expensive. If I have an application that has very spiky workloads, I don't necessarily want to be paying for a couple dozen GPUs at any one time. Another thing is if I'm on-prem and I have a fixed GPU resource, so let's say I have a 8 by H100 cluster, I have a bunch of stuff that I want to run on that. Maybe I have training jobs as well. Maybe I have different applications. By using scaling, I can free up my GPU for other uses. And I can deal with things like inconsistent response times that lead to a better application. Actually, all of these are the same reason, which is your application has some kind of goal. And typically, you can achieve that goal by optimizing your scaling. So here I have 3 different kinds of use cases, obviously generated. The images are generated by ChatGPT. But on the left, I might have an AI chatbot, something like the OpenAI ChatGPT chatbot. In this case, I'm optimizing for something like throughput or perceived latency for my user. I might have some kind of batch data processing and I'm using LLMs in that. In that case, maybe I'm optimizing for something like cost. And so I want to be sure that I'm using the minimal GPUs as possible. And then I have use cases where maybe it's only useful in business hours. So an application that is serving accountants and accountants work 9 to 5 or something. There I might be optimizing for throughput during 9 to 5 and then cost the rest of the time. So scaling is a way that you can achieve those goals that your application has. So I'm going to give a very brief introduction to scaling 101. So scaling more or less is a solved problem for non-AI based applications. And this is broadly how it works. So there's 2 types of scaling. There's vertical pod scaling and there's horizontal pod scaling. So vertical pod scaling is essentially if I have a higher load, I can swap my machine to having a machine that has more memory, more power, whatever it is. This is not the kind of scaling that I'm going to be talking about in this particular example, because what this would mean for AI workloads is provisioning a bigger GPU, which takes time, and it's just leads to downtime. It's just not the right way to manage this. But you can see this lovely graphic, which I took from Anvesh Mupeta's Medium blog, which is actually a very good blog as well. A way that you can think of vertical pod scaling is, if I was to explain it to my mother, it would kind of be like if I'm a restaurant and I'm getting more orders and I give my chef a bigger stove. That's kind of a way you can think about vertical pod scaling. Horizontal pod scaling is more like if I build more kitchens. So I have my workload deployed on a GPU somewhere, or a CPU in this case. And during times of high traffic, I either add more nodes, I add more instances, or I take away more instances. And this is the kind of scaling that's relevant for this conversation. So the key thing in this kind of scaling that I'm talking about, in horizontal scaling that I'm talking about, is metrics. And so when you're scaling up and down, your scaler needs to be able to know when you need to scale up and when you need to scale down. And that is all triggered by some kind of metric. Now, the metrics that we want to feed in is kind of the basis of the conversation that we're going to be having. So do I want to be scaling on CPU capacity or any other number of metrics? So serving is a solved problem when it comes to kind of traditional applications or non-AI based applications, because traditionally these metrics are things like CPU load. So, when my CPU is very busy, I scale up, and when it's not, I scale down. But this completely breaks down in the world of LLMs. And the reason why it breaks down is because AI workloads are GPU bound and really not CPU bound. So I can give you an example. So let's say I'm deploying an 8 billion parameter model on some H100, for example, making reasonable assumptions about what that workload might look like. I might get to 5 requests per second, which is not that many. But for a single GPU, and you'd have much bigger CPUs attached to this GPU, I might be able to process thousands of requests per second. So a single HTTP request is less than a millisecond to process. And these are just completely different orders of magnitude. So if I'm building my scaling to be able to scale up, scale down to ensure that I have the right performance of my application, I'm going to be completely scaling on the CPU would be a complete wrong metric to scale on, because my CPU won't get overloaded until way after my user experiences bad performance. So in AI, because all of the heavy lifting is done on the GPU side and not on the CPU side, traditional scaling mechanisms of using the CPU is not going to work. It's going to be a lagging indicator of when scaling would actually be required. And so this is going to break down completely. So we need to think about new and interesting metrics that we can scale on that are closer related to the performance that we would actually expect for AI. And this is actually a really hard problem. And the reason it's a hard problem is because actually the expertise are just in completely different places in your org. So I have this very friendly looking Kubernetes man, which stands for some kind of infrastructure engineer who knows a lot about infrastructure, knows a lot about building scaling systems, but doesn't know so much about AI. Doesn't know, for example, what bottlenecks AI performance. I have somewhere else in my system. It's very weird. It's like the female version of him, but it's like she's the data science one. So she knows a lot about AI, but doesn't know anything about infrastructure. And so she knows, for example, that my model performance is going to be bottlenecked by things like my KV cache, and he has no idea what a KV cache is. So there's this interesting problem here where the skill set and knowledge is kind of completely distributed within the org. So to solve this problem of how do you scale in AI, you need this kind of intersection of understanding how AI models work and how AI inference works, while also understanding the infrastructure side too. So I've called this, in this case, AI-aware infrastructure. So how do we build kind of things like auto-scaling for AI workloads? And the question goes back to what metrics do you want to be scaling on? So we don't want to be scaling on traditional metrics like CPU. What should we scale on? I'm going to give you 2 things that are very reasonable best guesses of what we might want to scale on. And I'm going to tell you that both of them might not be the best thing to do. And then I'm going to tell you the way that we solved it. So one kind of obvious guess is that maybe we should scale on something like GPU utilization. And this seems like a really, obvious thing to scale on because, if my GPU is really busy, then I should probably give my application more GPUs. And if it's not busy, maybe I can take away some GPUs. But the reason why this is really difficult is because the metrics that are actually published when you're from the GPU don't actually correlate well to true GPU utilization. So the metrics that are published from the GPU essentially say what percentage of the time is the GPU doing any work. And if you know anything about GPUs, you'll know that GPUs are really, really good at parallel processing. So it's not actually important to me if I know if it's doing one calculation. What's valuable to me is if I know if it's doing 1,000 calculations or if it's kind of run out of parallel processing. So if I was to scale on the published metric of GPU utilization, that would not be good because it wouldn't be able to differentiate, for example, between one batch running and 100 batches running. And so I wouldn't actually be getting the right sensitivity of when I need more GPUs or less GPUs. So GPU utilization is not the one to scale on. Another option is scaling on something like KV cache, which is more what LLMs are bottled by. So you would get kind of the right scaling behavior. The reason we don't do this is because it's very, very, very difficult to do well. So the KV cache representation for a llama model is different to a Gemma model, which is different to a Falcon model. So you have a different representation for every single model type. And I've got a different representation for every inference engine too. So my KV cache representation for VLLM is different to Olama, is different to SGLang, et cetera, et cetera. And so I have this all-to-all relationship between models and inference engines, which is very difficult to manage, especially if I'm an enterprise managing, say, even half a dozen different different models deployed. And although this isn't necessarily a concern now, but might be in the future, some models don't have KV caches. So this is a very transformer-specific metric to scale on. There are model architectures, for example, the Mamba series, which we're excited by, which if they took off, would make this useless since they just don't even have this metric to begin with. You can, another reason why we don't love this metric is it's also very difficult to explain to product folk. So if my product person tells me, okay, I want to be sure that my user never needs to wait more than X milliseconds for a response, talking to them about KV cache occupancy is just not going to be helpful for that conversation. So it's a very difficult kind of translation to actual product behavior. And for all of these reasons, we don't use this to do our scaling. Dynamo, which was announced by NVIDIA, does use KV cache occupancy for their scaling, so you can check that out. And they've just kind of made the decision to manage that all-to-all relationship, which we were a bit intimidated by. So instead of scaling with those other metrics that I talked about, we decided to make our scaling based on proxies. And these are proxies that, in theory, should be really good correlators to what the user is actually experiencing, to what's actually going on in the product. So we want to scale on proxy metrics, which are good estimates for when GPUs are actually busy, which translate, kind of to user experience. Is relatively straightforward to collect the metrics of. So we like resilience in our scaling systems, which is why we don't like to manage, for example, all-to-all metrics. And we also wanted to work with proxies that were very easy to interpret. So it should be an easy translation to talk to product folk and have that conversation with them of how do we want to make these scaling decisions. So for us, we decided to scale based on queue length, which is fairly straightforward. For each request, we track when the server receives and delivers the request. We take the difference between them, and then we turn that into a time in queue metric. We publish this metric, and we're able to scale on it when it's above or below certain thresholds. So when my time in queue is really high, we know that we need to be adding more GPUs. When my time in queue is very low or zero, and we know that we could be scaling down. And this works really, really well for us. It's probably about 90% as good as, for example, things like KV cache scaling, but it's just a very, very nice metric to scale on because it's a really good proxy of when the GPU is busy. It's very, very straightforward to work with. It's resilient to model type. So things like time in queue are kind of always going to be the case, dependent on if we have a llama model or if we have a Mamba model. This notion of how long do I have to wait is going to be consistent throughout all of them, which is nice. And it's very, very easy to explain as well. So it allows the teams who are working with our infrastructure to go to their product folk and say, okay, tell me about the kind of behavior you want this application to have. Does it matter if it takes 5 minutes to scale up, or do you want instantaneous responses? There's an additional complexity here of things like building scaling to zero, which is an interesting thing in itself, which maybe can be the next version of this talk. And so what this actually looks like is when I speak to my product people of how do we want the model to actually behave in production, which we can translate backwards to our scaling infrastructure, is a very easy conversation to have with them of, okay, do you want it to be super reactive to scale up, or are we fine maybe waiting for a couple minutes to scale up? So a common pattern that we see is we want things to be super reactive to scale up, so we don't have any time in those queues, but then maybe really, really slow and not very reactive to scale down, so we kind of maintain that very low latency experience. We might want different thresholds for when we're going to from 10 GPUs to 1 GPU to 1 GPU to 0 GPUs, because you get that cold start to go back up, and you might have different thresholds to go from 0 to 1 to 1 to 2. But this is a very easy conversation to have with a product person in a way that scaling on other metrics isn't as much. And so going back to the way that scaling works kind of in theory on a one-on-one basis, it essentially works pretty much the same when we're serving AI models and when we're scaling AI models. The only real difference is the metrics that we decide to scale on. And we think that a really good metric to scale on is queue length. So these scaling rules are really deeply linked with the application performance that we want and expect. So going back to my 3 applications from before, my AI chatbot, I might have really high sensitivity to scale up. So as soon as I have my anyone entering any queue, I want to scale up immediately. But maybe I never want it to scale to 0 because having, a 2-minute cold start time just isn't acceptable. Maybe for my batch data processing use case, I have very low sensitivity to scale up and scale to 0, because actually the thing that I care about is cost optimization and throughput. And then my application that is sensitive to business hours, maybe my application that's serving accountants, maybe I want it to be incredibly sensitive from 9 to 5, and then really not sensitive during business hours. And I'm happy for it to fall asleep for a couple hours overnight, as long as during the day it's really, really responsive. And that's a very easy conversation to have with those product folk. So going back to this concept of an inference system, the inference system is a lot of different components. But the most important thing is that every single component in your inference system should be built and optimized so that whatever application you're serving can deliver the value it needs to. But what we don't want to do is build a completely different inference stack depending on every single deployment. So you want an inference stack that's agnostic and flexible and allows product people to tune various parameters of I care about latency, I care about cost, or I care about throughput. And what this means is we can have one single inference stack that serves all of our workloads, but have it be flexible for the needs of the moment. So for those who fell asleep, you can wake up now. Going back to our TLDR, a inference system is much, much more than an inference engine. There's a lot more complexity that goes on to be able to deliver these scalable APIs. Traditional CPU-based scaling methods aren't appropriate for AI workloads, but you can use pretty much the identical pattern as traditional scaling. But if you change the metrics from things like CPU load to better proxies, like in our case, queue time, they're much better scaling metrics for AI. So I'm going to pause there. And we're also in luck that we have some of the team that actually did all of this heavy lifting at the back, if you want to talk to them in the break about any specifics. But otherwise, any questions? Yeah. So your question is essentially like, in most use cases, I'm not serving a single language model. I've probably got a bunch of different models, a bunch of different tools, a bunch of different, vector databases all together. How do I serve all of them how do I serve all of them, and do I need different strategies for each of them? That kind of a question. Cool. So I'll take the model piece first. So on the model side, most applications don't just have a single model that's deployed. So a RAG application can very reasonably have 4 different models. So maybe I have language models, guardrail models, an embedding model, a re-ranker model at the very least, and maybe I have fine-tuned variants of all of them. This applies to all of them, and the way that we kind of orchestrate it is that we have I might have an inference container for every single one of those models. And then my scaling manages all of those. And because all of those are GPU bound and they can share GPU resources as such. For vector database deployments, they typically happen on CPU. And so you need different scaling strategies for that. You wouldn't want to scale them in the same way that you would scale your models because they're just bounded by different things. Yeah. So I guess there's a difference in scaling between CPU bounded things and GPU bounded things.